to introduce Grigory Rozenblum. He is one of the scientists that do not need to be introduced, because everybody knows him because of his beautiful results. However, it's a great for me. It's a great pleasure to announce his talk. So Grigory Rozenblum from Chalmers University of Technology, Sweden, and earlier International Institute of Mathematics, Russia. Please, Grigory.
Thank you very much. Thank you for the introduction, and thank you for inviting me to give a talk here. I'm not in Moscow. I've been in Moscow last time, probably 5 years ago, before all the events, but now I'm morally there. So I'm going to talk about one of my directions of study. It was inspired by some technology, physical and technology problems. But the Neumann-Poincar operator, which is the main topic of studies, is the object which you taught your students in mathematical physics course, or probably in function analysis course. It's simply the double-layer potential operator. And recently there was a renewed interest due to the wave propagation in auxetics. These are some artificial materials with negative material constants. So it may be negative Poisson constant in elasticity, or it may be negative dielectric constant in electrical studies. The Neumann-Poincar operator, it will be written there, is different from the one you taught your students. The double layer potential in for the Laplace operator is a compact operator. We have discussed it a couple of days ago at this conference. But in elasticity, it's not a compact operator. It's a pseudo-differential operator of order 0 with 3 points of the central spectrum. So that my topic is to find something about what can be said about the eigenvalues convergence to these points. So something about pseudo-differential operators everyone knows. I don't need to repeat. Simply important that we are considering the vector case. So everything happens on a manifold gamma, and on n times, the symbol is n times n matrix, and it acts on n component vector functions. So the essential spectrum with the set of eigenvalues of the principal symbol. So this new J are eigenvalues, and so the essential spectrum is the union of closed intervals. Sometimes these intervals, it is the values of the eigenvalues of the principal symbol. And sigma, the essential spectrum, is the union of closed intervals. Our case is when all of these intervals degenerate to isolated points. So these are constant. By A0, we denote the principal symbol as the symbol of order 0. A minus 1 is the next one of order minus 1. So the operators are polynomially compact. This means that they are not compact themselves, but there is some polynomial p, so that the polynomial of this operator is compact. The essential spectrum consists of several points, which are the 0 points, the zeros of the polynomial, and these are points of the essential spectrum, and discrete eigenvalues may converge only to these, from above or from below, and we're going to count them. So what we're going to count, the important notation, probably the only notation. So let omega s be one of the zeros of this polynomial p. We fix some reference point tau minus, and for tau between 0 and tau minus, we denote but n minus of the operator omega s and tau, the number of eigenvalues of this interval. This is the representative of the picture. So this is the point of the essential spectrum, omega s. By stars, we denote the eigenvalues of the operator. We have two reference points. This reference point, both of them are to the left, omega s minus tau minus, and some moving reference point, which is noted by green, it's omega s minus tau. And we count the eigenvalues, the red ones, these ones, the red eigenvalues. And when tau goes to 0, this green reference point moves closer to the reference point, to the point of the central spectrum, and therefore the black eigenvalues become red. So we're interested in the behavior of this n minus, the number of red points, when this green reference point moves there. So it's denoted by n minus, and minus it means that we count the eigenvalues to the left. Similarly, there are n plus. It is we can count the eigenvalues which are to the right of the eigenvalues. And also this is denoted by n plus, these red eigenvalues. And also we're interested in eigenvalues, counting the eigenvalues n plus plus n minus. So the red eigenvalues here and the red eigenvalues here, as many as there are. So the operator is pseudo-differential with order 0, and we use the formula which had appeared at least twice, I think, at this conference. It's the Biermann-Slamek formula counting the eigenvalues of the compact operator of order 0. So if b minus 1 is the principal symbol of order 0, then this counting function, positive or negative eigenvalues, has the following formula. So here B is a matrix. So the sense of what's happening there is that we take this B minus 1, the symbol of order minus 1, take the positive or negative eigenvalues of this matrix, and take the sum of this positive or negative eigenvalues, and we get the leading coefficient in the formula for the counting function, and plus and minus. And if n, and there is an important property which will be used, that this formula says that if at some point just one of these eigenvalues of the symbol is positive or negative, then the corresponding integral is non-zero here. So if the integrand is non-zero at least at one point, since everything is nice, then the eigenvalues are, there are infinitely many eigenvalues of the corresponding sign. Also, the formula for the n of tau, so this means the positive sum of negative and positive eigenvalues, the coefficient has the following formula. So here one must simply take the absolute value of the matrix B. So these formulas were proved quite long ago by Biermann and Slamek in the 70s, and just last year there appeared the paper of our colleague at this conference, Raphael Ponch, who found a soft proof of this formula, which turned out to be very useful and widely cited. So, especially when d is an even integer, when the dimension d is an even integer, so here the integrand in this formula of trace is just the trace of the power of the matrix B minus 1. So it's polynomial function of the entries. So it can be controlled. When d is an odd number, so it's a hard thing to calculate. Well, so how we find the eigenvalues of the polynomial compact operator? So this essential spell consists of several discrete points. The eigenvalues converge to, we study the eigenvalues converging to one of these points. The approach consists that we guess a polynomial which distinguishes the eigenvalues which lie near the given point omega s, but almost destroys all others. And we guess
what does it mean? What does it mean?
Destroys, so it makes them much, much smaller in order than the eigenvalues which lie near this one.
It
So
vanishes.
sorry?
It vanishes at this point, or not at this point?
No,
Yeah?
not vanishes, but make them smaller in order. So they keep the order, the decay order of eigenvalues which lie near omega s, but they make smaller in order the eigenvalues which lie near other points. So this is the formula. I guess so one take the squares of this tau. There must be t here, but not tau. So one has degree 1 for this root and degree 2 to the others. And it is proved that, in fact, that the asymptotics of eigenvalues of the operator Bs, Ps of A, they have the same order as the eigenvalues of the operator A lying near omega s, but they do not feel other eigenvalues. So in the leading term, we have reduced the problem to the problem of studying the compact operators. Well, so when we have a concrete operator A, we take this operator P, we take this polynomial P, calculate the operator P of A, calculate its principal symbol, and then use Biermann-Slaymak formula. So from the point of ideas, it seems to be very, very simple. But when it comes to calculation, it's not that simple. I will present the expression for the principal symbol of the operator B. So B is the symbol of order. Operator B is an operator of order -1. Note, A is an operator of order 0, B is operator of order -1. I present it for the case when with what is interesting here. So D, the dimension equals 2, N, the dimension of the fiber, so the vector dimension is 3. Yeah, so there are 3 points of the essential spectrum, and the formula, so it's the case of interest. So gamma is a smooth compact two-dimensional surface, A0 is the principal symbol, A-1 symbol of order -1. So this is the polynomial, and the principal symbol of this P-1 is also here present. Some derivatives of the principal symbol, this terrible formulas. You do not need to read this formula. I just wanted to impress the audience that the formula for the symbol is this one, and must keep
impressed.
That all of them are matrices, 3 by 3 matrices. There are 24 terms. In fact, there should be 25 terms, but one of them fortunately vanishes. So in order to make some calculations for the elastic case, which we're going to study, one needs to make these calculations with symbols, and then to find the eigenvalues of the symbols, and then make integration. So now, not a very nice job. Well, now the application is the elasticity Neumann-Poincar operator. So elasticity, it is governed by the so-called Lamé-Navier equation. So here everything acts on 3 component vector functions. In the domain omega, say with smooth boundary, lambda and mu are material constants, the so-called Lamé parameters, and there is important parameter kappa, which is expressed via the Poisson constant of the material. So this is a system, an elliptic system of 3 equations with 3 variables. For this operator, so it is known the Kelvin matrix. It is the fundamental solution. It is known alpha and beta are expressed via the Lamé constants, and the conormal derivative is called traction. It is also some differential operator at the boundary, which also is expressed via Lamé constants. And the Neumann-Poincar operator is the double layer potential. Here it's a double layer potential. So it's you can just see that it is quite similar to what is written for your students in mathematical physics course. But here, the bad thing is that it is a matrix operation. So phi, this fundamental matrix, is matrix. T is a matrix operator. So even for a smooth boundary, this operator is not compact, since there are off-diagonal terms everywhere, which are not zero order, not compact. So in dimension 3, which is the most physical one, it was found, in a series of papers, it was found that the Neumann-Poincar operator, this integral operator which was written before, it is a pseudo-differential operator on the boundary. So boundary has dimension 2. Therefore, I talked about dimension 2 earlier, with such principal symbol. Look here. There's a principal symbol. Here there is the coefficient kappa 0, which is expressed via the Laplace constants. Psi prime is a cotangent vector to the boundary, and so this is the principal symbol. And the eigenvalues of this principal symbol, which govern the spectrum, are 0 and plus minus k0, kappa 0. So there are exactly three points of the essential spectrum, which just the case which was discussed a few minutes ago. So the dimension of gamma is 2, the dimension of the fiber is 3, and so it's easy to say that we are interested in finding the behavior of eigenvalues which approach these 3 points, and we should use this terrible formula with 24 terms. The operator is polynomially compact, and the polynomial which makes it compact is this following one. The essential spectrum of these 3 points, and the theorem, which is the easy part, which actually doesn't need to be proved just by some references, that the eigenvalues lambda n s, so n is numbering of eigenvalues, s numbers indicates to which of the points of the essential spectrum this eigenvalue converge. So from Bierman-Slamak formula, it follows that they converge as n to the power minus 1/2, and the counting function, which were discussed previously on the pictures, have the following asymptotics: some coefficients which depend on this s. It's the number of eigenvalue of the eigenvalue principal symbol on the surface, and on the Laplace constants, and they this t tau to pi minus 1. So it's the easy part, which follows just by composing references. Now we come to the hard part. The hard part is to find the geometrical and mechanical meaning of these coefficients. Why is it important? Just can say a few words, and I'm not sure I understand all of this quite well. You see, in the study, in the theoretical and then material studies of behavioral materials with wrong sign of physical constants, it was found. So first theoretical, and then such materials were practically constructed that at some relations between material constants of the material. So if you have some body with negative, for example, the electric constant, and positive neighborhood, some strange waves arise. These waves are called plasmon resonances. So some strange waves which go more or less surface waves, and they do not fall into the theory of usual materials. And it is some eigenvalue, these eigenvalues which we discussed, they just describe some characteristics of these plasmon waves, plasmon resonances. So it's important to find the geometrical mechanical meaning of this coefficient. So how to find these coefficients? So one need to calculate, we denote by M the principal symbol, so there should be S, not sigma, but S. So the principal symbol of the operator PS of K, and then substitute it into the Birman-Slamiak formula. So not an easy task, and the integrand is terrible. You see, one should calculate these 24 terms. One gets a matrix depending on quite a lot of parameters, then calculate separately positive and negative eigenvalues, and then integrate them. So here one can come just to qualitative results. But when it comes to n plus n-, so here, due to the fact that the dimension is even, then one simply should take the trace of the square of the matrix, which is calculable. Well, what was known previously, so about these eigenvalues? Just one single case, and very recently in 19, it was Dengli and Liu who calculated for the sphere, calculated the eigenvalues separated for the sphere. Here are these eigenvalues. They have high multiplicity. They are expressed via Lamé constants, and there are some observations which can see looking at this formula that all three sequences approach their limit points from above. There are no eigenvalues that approach this point from below, and it is the eigenvalues which approach from below which generate these plasmon waves. Moreover, the eigenvalues tending to zero, these ones, they do not depend on the material. This one depends on the material constants, but this one doesn't depend. So even this ball is not easy since variables do not separate. But the question is to find what of this remains and what of this is destroyed when we pass to the general body. So here the main theorem. I probably will not be able to say anything about how all of this proved, is the following. So let kappa, that chi and W are the Euler characteristic and the Willmer energy of the surface gamma. Euler characteristic everyone knows, and Willmer energy is the integral, it's written here, it's the integral of the surface of the sum of principal curvatures of the surface. Euler characteristics is the topological invariant, and the Willmer energy, it shows how strongly or weakly is the surface curved. Well, so in this case, it said that the coefficients in this expression of n are linear functions in these two geometrical quantities, where A and B are coefficients which do not depend on the geometry, they depend only on the material. Next, it follows that there are always infinitely many eigenvalues near each of these points omega s. Since these coefficients are universal, so this means they are the same as for the sphere, and for the sphere it is known that they cannot vanish simultaneously. Next, there are asymptotic formulas of this kind. The coefficients are given by explicit terrible formulas. The coefficient C plus, so describing the eigenvalues which approach the points of the essential spectrum from above, these eigenvalues, there are always infinitely many of them, just in this, as in the sphere case. These coefficients are always positive. Next, if there is just a single point where the surface is strictly concave, this means that then the coefficient C minus is positive. So if the surface is strictly concave, there are infinitely many eigenvalues converging to these omega s from below. In particular, if the body has a cavity, cavity inside, there are infinitely many such eigenvalues. Well, how it is proved? Just a few words. So this is the principal symbol, and in order to apply this terrible formula, at least to study it, one need to calculate the derivatives of the symbol in some coordinates system, and also the lower order symbol. And here again, this terrible formula. You see here are some red terms and blue ones, and it turns out that the red terms are the only one which depend on the geometry. The others do not depend on the geometry, and so it proves the structural theorem for the symbol. And so just by terrible analysis of the symbol, so the hardest part is to represent the Neumann-Poincar operator, which is an integral operator, as a pseudo-differential operator, which is made by some expansions. Oh, well, so one calculates the eigenvalue asymptotics by means of formula of Bierman-Salamiak, and here just in the formula for the coefficients there is present some universal terms, and the universality makes it possible to calculate the coefficients in the symbol for the easy case. So when the surface is a cylinder, and there a lot of terms disappear. There are still quite so next part after the dependence on the geometry is separated. Now the dependence on material. So how do these coefficients depend on the Lamé constants? And also can be found that these coefficients, they depend on the Lamé constants fractional quadratically, and the expression is found. So it's just one of the topics, one of the mathematical topics which arise there. Many questions keep, in particular, the pseudo-differential methods which are applied in this paper. They cannot distinguish between the case when there are no eigenvalues of some sign, say negative eigenvalues, or a finite number of eigenvalues of this sign. They cannot distinguish it. This is out of reach for pseudo-differential methods. So when we are interested in the topic, is there at least one negative eigenvalue? It requires some additional machinery which is not known. So here I want just to mention one question which is unsolved yet, even not for the Laplacian, not for the elasticity, but the usual Laplacian. So the double layer operator for the Laplacian, the one you taught your students many times, double layer operator. Question: when are there negative eigenvalues for this operator? At least one. The experimental material says that for the ball, there are no negative eigenvalues, but there are examples of some oblate ellipsoid where there are negative eigenvalues. And I popularize for some time this question. Find out just a little bit some conditions when the double layer potential for the Laplace operator in a three-dimensional smooth domain has or doesn't have negative eigenvalues. Well, there are some papers which are given here where this and quite a lot of other material is presented. You can see that quite fresh ones, and especially I want to direct you to the last one, the paper which was published in the Polish journal Postcolor Mathematics, because there we consider much harder case, the case when when the material of which the body is constructed is not homogeneous, but it's non-homogeneous. In this case, the operator is not polynomially compact anymore, and so it has the essential spectrum which fills some intervals and some eigenvalues which converge to the endpoints of this interval. And in this paper, one can see some machinery to study these eigenvalues which converge to the point of the machinery. So to the intervals. So that's, I think I left this information for sufficiently long. You know my name, so it's easier. Everything here is on the archive, and you can see everything there. So thanks a lot for your attention.
Okay, thank you very much. I hear some questions, remark, comments. Yes. Yes. Okay, somebody. And some oral comments. Do you have some oral comments? Some questions, some remarks. Okay. I hear some other problems. You are speaking about elasticity problems. I hear some other problems where you meet such zero-order operators.
Maxwell.
Maxwell also.
Yes.
And
so it may be Maxwell, it may be Stokes.
And for Maxwell operator, you have essentially the same results or different.
So theoretically, it must be the same, but it's not. It was not calculated. You see, it requires some calculations to find out the spectrum and so on. So again, both for Stokes and for Maxwell, one can consider the potential double layer potential operators, and they also are important in the isostatics field. And simply, it was not covered. It was not studied.
And what do you wait? I hear some new effects.
You see, I am interested only in mathematical point of view. What does all this mean for physics? I honestly do not know.
Yeah, I mean, yes, of course, but I mean mathematical effects.
So mathematical, I expect that for Stokes there will be the same, more or less the same result as for the Laplace, for the electrostatics, because probably no, it will be something like here, but with a different construction. Probably there will be five eigenvalues, which make the calculations much higher. For the Stokes, I think it will be the same. And of course, when you study the non-homogeneous media, it will become or even non-isotropic media. The approach works, the approach should work, but the calculation become even more terrible.
Okay, so the main problem is how to avoid such terrible calculations.
Yes, yes. Yes.
Okay,
so what I can do is to represent the integral operators. So they are singular integral operators as pseudodifferential. So hard calculations of the symbols.
Okay. Okay. Thank you very much. Okay. Let us thank the speaker. Okay, people. Okay. Somebody also.
Александр Александрович, у нас был еще один вопрос
Да?
онлайн-участника. Вот он поднимал руку, к сожалению, опустил уже. Я не знаю,
Да.
может быть, дадим слово.
Я не знаю, как ее, так сказать, как это на это ответить. Ну, давайте, может, он задаст вопрос опять?
Maybe there are some questions again.
Okay, let us thank the speaker. Well, everybody can send an email and get an answer. And I think the next speaker will now begin to prepare his talk. I mean, try to demonstrate, to share his screen. Okay, thank you very much. Thank you.